Welcome back, friends. Please remember on this channel I usually post math videos that are more advanced level or interesting and so on level. So here we're going to have the following integral, the definite integral that goes from 0 up to 6, and here's the integrand. It's going to be x times x minus 1, and then x minus 2, and then x minus 3, and then x minus 4, alright, and then x minus 5, and then x minus 6 dx. So we want to find the value of this integral. What we don't want to do definitely is try to multiply out all of these factors and form the polynomial and then anti-differentiate with the power rule. There has to very likely be some better way of doing it. So what is that better way? Well, let's just plot the integrand so we can motivate something here, okay? So let's plot this, x times x minus 1, and then x minus 2, and then x minus 3, and then x minus 4, and then x minus 5, and then x minus 6, and then see whether we can spot something. At first it looks like a bunch of nonsense. Let's zoom out here, okay, and let me just stretch this out also this way. So let's see whether we see anything that might be useful to us. Okay, so let's see. If I, for example, put a vertical line at 2, that's not useful because the piece to the left is different from the piece to the right. But if I put a vertical line at positive 3 there, it looks like it might have some kind of symmetry. Specifically, take a look, right? Like here, for whatever x, you have a negative y, and then for the opposite x, you have a positive y. This is an x and a positive y, and correspondingly, let's see, here you would have the negative x and the negative y. It looks like maybe we can use x equals 3 as a line of symmetry. So how do we actually make that in practice? What we can do essentially is just set u equal to x minus 3 this way. We're going to recenter essentially, and then let's change the limits of integration. We're going to have u is equal to 0 minus 3, which is going to give us a negative 3. When x is 6, then we're going to get that u is equal to, what was it, 6 minus 3, which is 3. These will be our new limits, and then x minus 3 will be replaced with u. So in other words, we can recreate our integral as follows. The definite integral that goes from negative 3 up to positive 3 with respect to u at least. U, take a look, go back over here, you see x. So from this replacement, we're going to say that u plus 3 is equal to x. So the x first will get replaced with u plus 3 this way. And then after that, where we have x minus 1, let's think about that. So you're going to do u plus 3 minus 1 is going to be a u plus 2. That transformed. And then where it says x minus 2, well, x is u plus 3, so it's going to be u plus 3 minus 2, which is going to give you a u plus 1. And then x minus 3 itself, that gets transformed into u directly. And then you repeat that on the other side, right? So for example, look, x minus 4, when x is u plus 3, it's going to be u plus 3 minus 4, which is going to be a u minus 1 this way. And then u minus 2, and then again u minus 3 all the way across, you see? And then when you differentiate here, since our transformation is u equals x minus 3, when you differentiate here, of course, right, we're going to get that du is equal to dx. So that means you end up with a du in this position. But now we've transformed this. Does this have any desirable quality or characteristic or property that will allow us to find the value of the original integral pretty easily? And what it does have is the following. It's odd. Since integrand is odd, we know the value is 0. Simple, you see? Once we have that characteristic recognized. In other words, since this is equal to 0, then this tells us that this right here, the original, is also equal to 0, and we didn't have to do any crazy multiplying out of all of the factors to form a polynomial. Oh, in case you're not convinced that this is odd, just by inspection alone in terms of the integrand, well, take a look at it. The picture shows it, but let me just do the following. Okay, imagine instead we have u plus 1, u in the middle, and then u minus 1 this way. A simplified version, okay? So look at it. You see this? It looks like it's odd, correct? For each x there's a y, and then for the negative x there's an opposite y. This is for the case of u plus 1 times u minus 1. Even if you did u plus 2 this way, and you did u plus 1, and then u in the middle, and then you did u minus 1, and then you did u minus 2 this way. That's our integrand. Imagine that's it. Then you see, that's the green curve. It would still have the same characteristic of being odd. And likewise with our specific one right here, that I created. So that's really it. In other words, using the oddness of an integrand after you've transformed the original to find the value pretty easily. Please leave a like and subscribe if you like math videos at this more advanced or abstract level.